All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Neil Armstrong reporting the roll and pitch program, which puts Apollo 11 on a proper heading.
Active FM, a big cheer to you for tuning in today. Whether it's your first time or you are coming back again, welcome to the show. This is The Void Show, and it is a family of people who are willing to learn new things every day, right? Because truth is, and I'd want to believe that nobody knows everything, right? So everyone or every person you meet along the way has surely went through something that you could not even think of, right? So those who learn the best, or those who live life differently, are those who really see themselves as students, okay? They are those who take every opportunity as a chance to learn stuff, or are those who take every chance as an opportunity to learn new things, okay? Hence I'm saying a big cheer to you. That's because you are here, because you want to learn new stuff, right, about our natural world, okay? And essentially that's really what science is all about. It's about discovering things. It's about understanding. That's the word. It's about understanding our natural world, okay? You want to come and debate about whether to believe in science or not. If you want to believe it, do it, right? But our goal is more of understanding our natural world. And you're going to see what we're speaking of today, right? You will see that it's really about understanding our natural world and really using our knowledge to make our life better. Okay, you will see when we speak about electricity, right? It's somehow going to squeeze itself in today's discussion. You will see really we've got electricity because we understand that, our knowledge can really be used to make electricity, right? So that's pretty much all our goal, right? It's really to understand our universe. It's a journey. It's an adventurous journey. So this is The Void Show, and my name is Andrew, and I'm so excited for today, right? So we've been speaking about some of the basic things one should know to learn, or before learning quantum theory, okay, or quantum mechanics. Now, we also said that if you've got no clue what quantum mechanics is, this is your show, okay? You want to listen to this, right? Because it's one of the most interesting subjects or courses, whatever, right, in physics, okay, or in chemistry. So you really want to listen to this. Now, we started off by speaking of matter, okay? Matter. We said matter is anything and everything that has got mass and has a volume. Okay, so if it has mass and if it has got volume, and by volume we mean the amount of space it takes in this universe. Okay, so anything that has got mass and a volume, it's a matter, right? You are matter, right? The tool you're using to listen to this is matter, okay? We also spoke about different states of matter, right? So in this universe, matter can exist. It can either be a solid, or it can either be a liquid, or it can either be a gas, or it can either be a plasma, okay? The sun and all other stars in the universe are made of plasma, okay? But when we speak of a solid matter, of a solid object, we're speaking of something that's solid, okay? That means it has a fixed shape and it has got a definite volume, okay? When we speak of a liquid has no fixed shape, but it has got a definite volume, right? That's because it literally takes amount of space in this universe. But it has got no fixed shape because it literally just takes whatever shape of an object it is inside of, right? Water is a liquid, right? But it has got no fixed shape, right? You put it in a cup, it takes the shape of a cup, right? You put it in I don't know, in a container, a pear-shaped container. It's gonna take the shape of that container, right? So it has got no fixed shape, but liquids have a definite volume, right? By that we mean we can measure the amount of space they take in this universe, right? We've got gaseous states of matter, right? So we now know that matter can exist as solid, it can exist as liquids, or it can exist as gas, right? So what is gas? You see, one interesting thing about gas is that it has no fixed shape and it has got no definite volume. Okay? For example, let us say you have a bottle of a gas, right? So it's a gas inside a bottle. For example, let's say ammonia, right? So ammonia is a form of gas. If you literally open that bottle of ammonia, maybe you are at a certain corner of your room, literally a few minutes later, that gas is going to be smelling all over the room. Okay? So that tells us that gases do not have a fixed shape, okay? They do not have a volume, a fixed volume, right? But they literally everywhere. Like the example we mentioned of what? Of a gas, right? Of ammonia. You would also speak about other gases as well. And the last gaseous state of matter, the last state of matter would be plasma, okay? Your stars or the sun, those are plasma. They are made of plasma, okay? We essentially refer to it as a fourth state of matter, okay? And that one is like, it can only exist in millions of degrees, right? Very, very, very high temperatures, okay? So that's pretty much what we spoke about. And after this, we're going to be extending on that. Really interesting stuff that you don't want to miss. We're going to be speaking about atoms, nuclear energy, okay? And there's this famous equation of Albert Einstein. You surely have seen it. E equals mc squared, right? You surely have seen that. If you haven't seen that, we're going to be speaking about it. So really, we're going to be speaking about so many interesting things today, right after this. Stay tuned.
Do you love radio?
Well, of course, if you're listening to
Music is hot music.
That's how it is and that's how it goes.
For all your information
and all your entertainment. Radio has never been better.
Right, so let's do this, okay? By now, you would know that anything in the universe can either be one of the four states of matter, okay? So by now, you would know that anything in the universe can either exist as a solid object, it can be a liquid, it can be a gas, or it can be plasma, right? By now, you know that. And one cool thing that you should also know is that we can have different states of matter transforming or turning into different states of matter, right? And that's when we speak of physical changes that can literally take place. And what do we mean by that? We mean we can have a solid object turning into a liquid object, right? We can also have a liquid matter turning into a gas matter, right? For example, a physical change that can take place. Let's say you've got a piece of an ice, right? A piece of an ice. You just took it out of your fridge, and ice is obviously a solid object, right? It's obviously what? It's obviously a solid object. Now, here's a big question. You tell me, what's going to happen if you start giving this piece of an ice heat, energy? What's going to happen? It's obviously going to start to melt, hey? And when it starts to melt, this solid piece of an ice is going to turn into what? It's going to turn into liquid, hey? What is this liquid? This liquid is water. So you already see a transformation that's taking place there. But what's going to happen if we start giving this water more heat energy? What's going to happen? It's going to start to boil, and boiling is that process when now this liquid water is going to now turn into what? It's going to turn into gas. In that case, what is this gas? It's steam. So the point that we're really trying to drive home here is that you can have different states of matter turning into other forms of matter, right? And this example that we just made of an ice, that's a physical change, right? You see what's happening. An ice is turning into water, and it's turning into steam, right? That's a physical change. But we can also have chemical changes, And essentially, chemistry is the study of these physical changes, okay? They study on how we can use these physical changes. And I'll tell you what, not physical changes, I mean chemical changes, Chemistry is the study of these chemical changes that are taking place, They study on how we can use these chemical changes, okay, for our life. Because I'll tell you what, chemical changes really do have practical purposes. For example, chemical changes normally produce energy. For example, let me tell you this. We burn wood to produce energy, okay? We burn oil, we burn coal to produce electricity, okay? So that's a chemical change that's taking place there, okay? It's from wood, it's from oil, it's from coal to produce electricity, to produce this electrical energy that we can use for our lives, okay? So that's really pretty much it. So here's an interesting story. And we are now speaking of laws that early scientists put into place, okay? But they suddenly changed as soon as Albert Einstein came into the picture, okay? You would know Albert Einstein. So back in time, like in the 1800s and stuff, there was a law of science that scientists put in place, okay? And if we should know, if it's a law, it's a law, okay? It's proven by either mathematical analysis, mathematical models, and by observation as well. Right? We speak of law of gravity, right? We see it happening, and you cannot deny it. You cannot defy it, right? That's why we're saying it's a law. It applies, whether you believe it or whether you don't believe it, right? It applies. Now, based on observations that scientists did in the past, they put a law. And this law is called the law, it's called the law of conservation of mass, okay? It's called law of conservation of mass, conservation of matter, right? So what it said is that you cannot create mass and you cannot destroy mass. But mass can only be turned into other forms of mass. Okay? What do we mean by that? We mean you cannot create mass. I mean, I thought I would say something differently, but it's pretty much the same thing. You cannot create mass or you cannot destroy mass, but you can just transform a mass or matter, an object, into other forms of matter, right? So what does this mean actually? It means that for example, let's say you are building a house, right? Let's say you are building a house, a good example. Now, this law means that the sum amount of the ingredients that you use to build your house is going to equal the mass of your house as a product. Do you get that? So if you're building a house, you're essentially going to be using bricks, maybe a bit of cement, windows, I don't know, tiles, right, ceiling. So what this law means, it means that you're going to get a house as your product, right? And if you take the mass of your house, and if you take the mass of your ingredients, they should be equal. They should be equal. There shouldn't be some extra mess that you now magically find in your house, right? They should really be equal. Let's take a bit of a scientific example. If you have a piece of a copper wire, right? Let's say you are heating a piece of a copper wire maybe in a flame, okay? Now, what's going to happen? Now, your piece of wire is obviously going to react with oxygen in the air, right? Now, what's going to be the result of that? The result of that is basically going to be what we call a copper oxide, okay? You take a copper wire, you heat it on a flame, right? So there's going to be a reaction that's taking place there. And the result of that experiment that you're doing is going to be what we call a copper oxide, okay? And this copper oxide is basically, it's going to be this black wire, black substance, okay? So this law, when it applies here, it means that copper oxide, which means your result is going to have exactly the same mass of copper and oxygen, right? There's no additional matter that's going to be created, and there's no additional matter that's going to be destroyed, okay? But what happened? Copper wire basically changed into something else. There was a transformation that took place, okay? So that's what the law of conservation of mass says, okay? And basically scientists, like in the 1800s, they tested the truth of this phenomena again and again and again, so sure that they knew that, you know, matter cannot be created nor destroyed, but you can literally just change it into that. And they put that law, right? They stated it as the law of conservation of matter, okay? And in those early times, scientists concluded that it's the same thing that applies with energy, okay? That basically means energy might change from one form to another form, right? Which means you can change maybe heat energy into electrical energy, into sound energy, right? So it's pretty much those things. You can change another form of energy to another form of energy, right? You literally can change energy from one form to another, but you can neither create or destroy energy, right? So they put that law into place, and that law also came, it was called the law of conservation of energy. Okay, so those were two separate laws back in time, hey? Now, in 1905, a great physicist of all time came into the picture. It's Albert Einstein. Now, Albert Einstein worked out a theory that showed that, listen to me carefully. Listen carefully. Now, Albert Einstein, he worked out a theory, okay? He figured out a theory that showed that matter and energy are not entirely different things as had previously been believed. You get that? So he showed that matter can be converted into energy, and energy can be converted into matter. Eh? And actually, when you look at that equation, right, of Albert Einstein, it's a very famous equation. We're going to post it on our The Void Show page. It says E equals to mc squared. Now, M, it stands for mass, right, for matter. E is for energy. So matter and energy can really work interchangeably, right? So that's pretty much what it is, eh? It shows that matter is really a very rich form of energy. That's pretty much it. So in Albert Einstein's proposal, it's also the same thing. So if you see what Albert Einstein did, he merged these two separate laws, the law of conservation of mass and the law of conservation of energy. He merged them together, and he was like, no, this is actually the law of conservation of mass and energy. The sum total of mass and energy cannot be reduced and destroyed. That's what Albert Einstein did. So I'm pretty sure that you understand what we're speaking of, because we really made good examples of what those different two laws mean, right? So what Albert Einstein did, he just merged them together to form this unified a law of mass and energy, right? And that's essentially what that famous equation means, okay? And what you should also understand is that the kind of mass into energy transformation that we're speaking of, that Albert Einstein discovered, I mean, we're not speaking, it does not occur in your ordinary physical changes or your chemical changes, right? It does not occur. We really are speaking of profound changes that occur at the level of subatomic particles, okay? Protons and your neutrons and your electrons. We're speaking of that. It's probably a time for a song. And here Asarela saying to you, Good Shepherd. Stay tuned.
You, Lord, are my shepherd, I shall not want. You make me lie down in green pastures. Your love is a resting place for me. And the oasis of peace to my soul. You have never left my side. You guide me through the night. You restore all that is broken inside. Oh, good shepherd, you are. Oh, good shepherd, you are. You open before me the way. Even when I walk through the valley of death, fear will never conquer me, for you already have. You are close and you lead me all the way. You have never left my side. You guide me through the night. You restore all that is broken inside.
Good Shepherd playing on a radio station that is Active FM, as we all and always say that radio has never been better. Thank you so much for still being here. I always say it feels great to have you around, and I mean, if you're still here, it means you are really loving what we're speaking about today. And really what we're essentially doing, we want to understand our natural world, right? But for today, what we really are discussing is matter and some of the properties of matter, right? I mean, before this beautiful jam, Good Shepherd, we really spoke a little bit more deeper, right, about what matter is, okay? And essentially what you should take there is that in physics, the word matter, its definition is really totally different from how we normally use the word matter, right? So our normal day use of the word matter would be what's the matter? Okay, that would imply what's the problem, what's the issue, right? But really in physics, when we speak of matter, we're speaking about anything. Okay, it has to exist, of course, right? It has to exist. If it exists, it is matter, right? It has to have mass. Okay, it has to exist. So if it exists, it means it's occupying some space in this whole universe, right? So, and I'll tell you a bit of a joke, which actually the title of the show today was taken from. So now you know what matter is, right? It's anything that exists. It's anything that has got mass, and it should obviously occupy some space in this universe, which obviously means the same thing as existing. But then I say to you, okay, hey, you've got mass, you exist, and you occupy some space in this universe, so you matter, right? That's a joke that's usually made in the physics. And by the way, this is the Void Show. I am your host, Andrew, and what we're gonna be ending with today is speaking a bit about atoms, right? Atoms, in the simplest, the basic definition of what an atom is a building block of everything. Okay, it's a building block of everything, and you're really gonna see what we mean when we say that. Now, let us go back a little bit, okay, to like 2,500 years ago to about 2,700 years ago, okay, roughly around those times, because those are the times when the word atom was first used, okay, or when the word atom was really brought into life. And so the word atom actually comes from the Greek, okay, and when you take it to English, that means not cut, okay. It's coming from the Greek words meaning not and cut, right? Atom is coming from the Greek words meaning what? Meaning not and cut, okay? And this word was actually it was coined, or it was the first person to come up with this word was the Greek philosopher, okay? Greek philosopher Democritus, okay? I hope I said that really well. And basically, Democritus was the first person to suggest that everything in the universe, by that we mean all matter in the universe, any physical substance in the universe can ultimately be broken down into tiny particles that cannot or could not be further broken down. Okay? So what does he mean by that? He means if you could take something and you want to break it down into pieces, you want to divide it into pieces, there will be a point when you would have ultimately broken down everything, like ultimately broken down this thing, this physical substance. There will be a time where you would have just, ultimately broken it down into tiny particles that you could no longer divide or break down this object into smaller pieces. Okay? So he called those smaller last pieces of objects that you broke down into what? He called them atoms. Okay? So essentially, again, if you could gather and collect these atoms together, put them together, you will essentially get what? This bigger thing that you broke down. Okay, so that's essentially what an atom is. Okay, today we know that an atom is made up of what? It's made up of what we call subatomic particles, right? So if you hear us keep saying subatomic particles, you should know that we mean of what we're speaking about, what makes an atom. Okay. So another thing that you might just want to know is that if you break an object down to its subatomic particles level or to its atoms level, those atoms, they literally gonna possess the same properties of the bigger substance, right? That you really have broke down. For example, and this is one of the most popular examples that's made in the physics world. Let's say you've got a silver, okay? If you have a silver and you literally divide it into smaller and smaller particles, you will eventually, right, finally come to the smallest particle, okay? But that smallest particle is not going to be different from the big silver that you initially had, okay? It will still show the same physical properties, the same chemical properties as the original and the first silver that you actually had. Okay, yeah. So that's pretty much what an atom is, and that's really what happens with atoms. But now. If you have groups of atoms, right? Or maybe if you've got atoms that are grouped together naturally, okay, it's really rare. And I've never heard of such a case where somebody has found a single atom, right? So naturally in this world, in the universe, we find atoms existing in groups, okay? We find atoms existing in groups, and these groups of atoms are called what? They are called molecules, okay? That's what they are called. Now, this is what you will have. You essentially have atoms of the same type combining together in a group with one another. They form what we call a molecule, right? They form what we call a molecule or molecules, right? Of a certain chemical element, okay? So in the past few weeks we spoke about the periodic table, okay? Last I checked, there are about 113 distinct elements, okay? In the periodic table. So each element is basically, for example, let's speak of a hydrogen element. A hydrogen element, if you want, you can say it's a hydrogen molecule. Okay? It's a hydrogen molecule because essentially what's there, it's groups of atoms of the same type coming together to form hydrogen molecule. Okay, so that's what it is. Okay, we spoke about the history of the periodic table, right? So every element is a molecule, right? So you essentially have a bunch of atoms coming together of the same type to form what? To form a chemical element or to form a molecule, right? A hydrogen molecule. You name them. So I really did say, last I checked, there were about 133 chemical elements. There are some of them that really occur naturally on Earth. Okay, they occur naturally on Earth. And literally, what is the periodic table? The periodic table is chemical elements that form all the known substances in the universe. Okay, all the known substances in the universe. Okay, oxygen, aluminium, potassium, sodium, magnesium, calcium, silicon, chlorine. So those are just a few of the examples, right? That really form all the known materials in the universe. Those are just the basics ones that really naturally exist on Earth. Okay, that really exist on Earth. There are some that they're rarely found. Okay, they are really found. They make less than 1/1000th of atoms on Earth. Okay, so they are really found. And that's when we speak about molecules, atoms like your xenon, right? Your iridium, right? Your promethium, your polonium, right? There's protactinium, something like that. So those are the rarest, right? Elements that are on Earth, right? So that's pretty much it. And over the years as well, we now have elements that are artificially made. Okay, that are artificially made. But one of the disadvantages of them, we've got people who made elements, other forms of elements. Okay, and those are called artificial elements, right? They basically made using nuclear reactors and stuff, but they are not stable. Okay, they are not stable. By that we mean they break down. Okay, they break down. So if they break down, they break down to other stable elements. Okay, so that's pretty much it. And a good analogy that you can think of chemical elements, a good analogy for that would be, think of the alphabets, right? English alphabets, A, B, C, D, E, F, G. English words are made of those. They're made of those. Each letter, right? Those alphabet, right? So you can think of chemical elements like that. Each one is separate, but when you combine them, you form something else. Okay. So now here's the thing that we're gonna end with. When different types of molecules combine together, they form what we call compounds. All right, they form what we call compounds. For example, water is a compound. Did you get that? So a chemical name for water is what? It's H2O, right? That's hydrogen oxide, right? It's H2 subscript 2 O, and H is what? It's 2 hydrogen atoms, 2 hydrogen molecules, and one oxygen molecule, right? So when you combine those, you get water. That's what makes up water, right? 2 hydrogen atoms and 1 oxygen molecule, right? So that's what water is, and we call that a water compound, right? Another example is table salt. Okay, table salt. That's it's sodium and chlorine that makes table salt, and the chemical element of table salt, the salt that we have, that's Na, which is sodium, Cl, which is chlorine, right? So that's really what makes up water, and that, remember, it's sodium molecule, chlorine molecule. Those are 2 molecules coming together. They form what? They form a compound, right? But if it's single, it's a molecule or atoms. Okay, so that's pretty much it for today, and I really hope that you learned a lot of stuff. I even do see that we got a bit ahead of time, but then right after this, we will essentially be closing.
What is active worship?
What?
Hello, Active FM. My name is Riabetsu Milao, and I am part of Active Worship. Active Worship is a group of kingdom builders who use their instruments and vocals as another means to glorify God and have recorded thus far 12 great albums. And I am so privileged and honored to be part of the team. I get to sing back up, I write songs and lead worship, and it's just been an overall blessing to me. So yeah, I'm very grateful for Active Worship.
Well, I think it's time for you to go and listen.
And apparently we have reached the end of the Void show today. I enjoyed the show. I mean, I hope you did. Remember, our goal is to understand our natural world, okay? To get a perspective, to get a perception, to know about our natural world, right? So, essentially today what we spoke about, you know what matter is, you know different states of matter, solid, liquid, gas, plasma, right? Stars, we didn't speak about stars a lot today, but stars are literally made of plasma, okay? That's the fourth state of matter, okay? You literally get it in high degrees of temperatures, millions degrees of temperatures, and we spoke about an atom. You know what an atom is, you know what molecules are, you know what compounds are. You now know what a chemical element of water is. It's hydrogen molecules, 2 hydrogen molecules, and 1 oxygen molecule, right? It's a water compound, okay? We've got you now know salt that you use at home. What's the chemical name of that salt, right? It's sodium chloride, okay? So that's pretty much it. I hope today you really enjoyed the show, and I mean, do not forget to share the show. From us, Active FM, The Void Show, we're definitely going to be seeing you next week, same time, same place, and we're really going to be bringing you fun and crazy facts about the universe. So all the love from Active FM. Have a fantastic week ahead of you.
Enjoying the Active FM shows? Well, then catch us on Instagram at ActiveFM777, Twitter and Gab at ActiveFM, Facebook at ActiveFM/777, as well as YouTube at ActiveFM and our website at www.activefm.co.za. Don't stop, don't hesitate. Find, follow, and enjoy us on all our different platforms. You don't want to miss out.
Active FM. Radio has never been better.